Air Traffic Control, ATC services. Besides the services provided by an FSS, as discussed in Tutorial 12, Aviation Weather Services, numerous other services are provided by ATC. In many instances, a pilot is required to have contact with ATC, but even when not required, a pilot finds it helpful to request their services. Primary radar. Radar is a device which provides information on range, azimuth, and/or elevation of objects in the path of the transmitted pulses. It measures the time interval between transmission and reception of radio pulses and correlates the angular orientation of the radiated antenna beam or beams in azimuth and/or elevation. Range is determined by measuring the time it takes for the radio wave to go out to the object and then return to the receiving antenna. The direction of a detected object from a radar site is determined by the position of the rotating antenna when the reflected portion of the radio wave is received. Modern radar is very reliable and there are seldom outages. This is due to reliable maintenance and improved equipment. There are, however, some limitations which may affect ATC services and prevent a controller from issuing advisories concerning aircraft which are not under his or her control and cannot be seen on radar. The characteristics of radio waves are such that they normally travel in a continuous straight line unless they are bent by atmospheric phenomena such as temperature inversions, reflected or attenuated by dense objects such as heavy clouds and precipitation, or screened by high terrain features. ATC Radar Beacon System, ATC-RBS. The ATC Radar Beacon System, ATC-RBS, is often referred to as secondary surveillance radar. This system consists of 3 components and helps in alleviating some of the limitations associated with primary radar. The 3 components are an interrogator, transponder, and radar scope. The advantages of ATC-RBS are the reinforcement of radar targets, rapid target identification, and a unique display of selected codes. Transponder. The transponder is the airborne portion of the secondary surveillance radar system, and a system with which a pilot should be familiar. The ATC-RBS cannot display the secondary information unless an aircraft is equipped with a transponder. A transponder is also required to operate in certain controlled airspace, as discussed in Tutorial 14, Airspace. A transponder code consists of 4 numbers from 0 to 7, 4,096 possible codes. There are some standard codes, or ATC may issue a 4-digit code to an aircraft. When a controller requests a code or function on the transponder, the word squawk may be used. This figure lists some standard transponder phraseology. Additional information concerning transponder operation can be found in the AIM Chapter 4. Radar Traffic Advisories. Radar-equipped ATC facilities provide radar assistance to aircraft on instrument flight plans, and VFR aircraft provided the aircraft can communicate with the facility and are within radar coverage. This basic service includes safety alerts, traffic advisories, limited vectoring when requested, and sequencing at locations where this procedure has been established. ATC issues traffic advisories based on observed radar targets. The traffic is referenced by azimuth from the aircraft in terms of the 12-hour clock. Also, distance in nautical miles, direction in which the target is moving, and type and altitude of the aircraft, if known, are given. An example would be traffic 10 o'clock, 5 miles eastbound, Cessna 152, 3,000 feet. The pilot should note that traffic position is based on the aircraft track and that wind correction can affect the clock position at which a pilot locates traffic. This service is not intended to relieve the pilot of the responsibility to see and avoid other aircraft. In addition to basic radar service, Terminal Radar Service Area, TIRSA, has been implemented at certain terminal locations. TIRSAs are depicted on sectional aeronautical charts and listed in the AFD. The purpose of this service is to provide separation between all participating VFR aircraft and all IFR aircraft operating within the TIRSA. Class C service provides approved separation between IFR and VFR aircraft and sequencing of VFR aircraft to the primary airport. Class B service provides approved separation of aircraft based on IFR, VFR, and/or weight, and sequencing of VFR arrivals to the primary airport. Wake turbulence. All aircraft generate wake turbulence while in flight. This disturbance is caused by a pair of counter-rotating vortices trailing from the wingtips. The vortices from larger aircraft pose problems to encountering aircraft. The wake of these aircraft can impose rolling moments exceeding the roll control authority of the encountering aircraft. Also, the turbulence generated within the vortices can damage aircraft components and equipment if encountered at close range. For this reason, a pilot must envision the location of the vortex wake and adjust the flight path accordingly. During ground operations and during takeoff, jet engine blast, thrust stream turbulence, can cause damage and upset smaller aircraft at close range. For this reason, pilots of small aircraft should consider the effects of jet engine blast and maintain adequate separation. Also, pilots of larger aircraft should consider the effects of their aircraft's jet engine blast on other aircraft and equipment on the ground. Vortex generation. Lift is generated by the creation of a pressure differential over the wing surface. The lowest pressure occurs over the upper wing surface and the highest pressure under the wing. This pressure differential triggers the roll-up of the airflow aft of the wing, resulting in swirling air masses trailing downstream of the wingtips. After the roll-up is completed, the wake consists of two counter-rotating cylindrical vortices. Most of the energy is within a few feet of the center of each vortex, but pilots should avoid a region within about 100 feet of the vortex core. Vortex strength. The strength of the vortex is governed by the weight, speed, and shape of the wing of the generating aircraft. The vortex characteristics of any given aircraft can also be changed by the extension of flaps or other wing configuration devices, as well as by a change in speed. The greatest vortex strength occurs when the generating aircraft is heavy, clean, and slow. Vortex behavior. Trailing vortices have certain behavioral characteristics that can help a pilot visualize the wake location and take avoidance precautions. Vortices are generated from the moment an aircraft leaves the ground until it touches down, since trailing vortices are the byproduct of wing lift. The vortex circulation is outward, upward, and around the wingtips when viewed from either ahead or behind the aircraft. Tests have shown that vortices remain spaced a bit less than a wingspan apart, drifting with the wind, at altitudes greater than a wingspan from the ground. Tests have also shown that the vortices sink at a rate of several hundred feet per minute, slowing their descent and diminishing in strength with time and distance behind the generating aircraft. When the vortices of larger aircraft sink close to the ground, within 100 to 200 feet, they tend to move laterally over the ground at a speed of 2 to 3 knots. A crosswind decreases the lateral movement of the upwind vortex and increases the movement of the downwind vortex. A tailwind condition can move the vortices of the preceding aircraft forward into the touchdown zone. Vortex avoidance procedures. Landing behind a larger aircraft on the same runway. Stay at or above the larger aircraft's approach flight path and land beyond its touchdown point. Landing behind a larger aircraft on a parallel runway closer than 2,500 feet. Consider the possibility of drift and stay at or above the larger aircraft's final approach flight path and note its touchdown point. Landing behind a larger aircraft on crossing runway. Cross above the larger aircraft's flight path. Landing behind a departing aircraft on the same runway, land prior to the departing aircraft's rotating point. Landing behind a larger aircraft on a crossing runway, note the aircraft's rotation point and, if that point is past the intersection, continue and land prior to the intersection. If the larger aircraft rotates prior to the intersection, avoid flight below its flight path. Abandon the approach unless a landing is ensured well before reaching the intersection. Departing behind a large aircraft. Rotate prior to the large aircraft's rotation point and climb above its climb path until turning clear of the wake. For intersection takeoffs on the same runway, be alert to adjacent larger aircraft operations, particularly upwind of the runway of intended use. If an intersection takeoff clearance is received, avoid headings that cross below the larger aircraft's path. If departing or landing after a large aircraft executing a low approach, missed approach, or touch-and-go landing, since vortices settle and move laterally near the ground, the vortex hazard may exist along the runway and in the flight path, particularly in a quartering tailwind. It is prudent to wait at least 2 minutes prior to a takeoff or landing. En route, it is advisable to avoid a path below and behind a large aircraft, and if a large aircraft is observed above on the same track, change the aircraft position laterally and preferably upwind. Collision avoidance. 14 CFR Part 91 has established right-of-way rules, minimum safe altitudes, and VFR cruising altitudes to enhance flight safety. The pilot can contribute to collision avoidance by being alert and scanning for other aircraft. This is particularly important in the vicinity of an airport. Effective scanning is accomplished with a series of short, regularly spaced eye movements that bring successive areas of the sky into the central visual field. Each movement should not exceed 10 degrees, and each should be observed for at least 1 second to enable detection. Although back-and-forth eye movements seem preferred by most pilots, each pilot should develop a scanning pattern that is most comfortable and then adhere to it to assure optimum scanning. Even if entitled to the right-of-way, a pilot should yield if another aircraft seems too close. Clearing procedures. The following procedures and considerations should assist a pilot in collision avoidance under various situations. Before takeoff, prior to taxiing onto a runway or landing area in preparation for takeoff, pilots should scan the approach area for possible landing traffic, executing appropriate maneuvers to provide a clear view of the approach areas. Climbs and descents. During climbs and descents in flight conditions which permit visual detection of other traffic, pilots should execute gentle banks left and right at a frequency which permits continuous visual scanning of the airspace. Straight and level. During sustained periods of straight and level flight, a pilot should execute appropriate clearing procedures at periodic intervals. Traffic patterns. Entries into traffic patterns while descending should be avoided. Traffic at VOR sites. Due to converging traffic, sustained vigilance should be maintained in the vicinity of VORs and intersections. Training operations. Vigilance should be maintained and clearing turns should be made prior to a practice maneuver. During instruction, the pilot should be asked to verbalize the clearing procedures. Call out clear left, right, above, and below. High-wing and low-wing aircraft have their respective blind spots. The pilot of a high-wing aircraft should momentarily raise the wing in the direction of the intended turn and look for traffic prior to commencing the turn. The pilot of a low-wing aircraft should momentarily lower the wing and look for traffic prior to commencing the turn. Runway incursion avoidance. A runway incursion is any occurrence in the airport runway environment involving an aircraft, vehicle, person, or object on the ground that creates a collision hazard or results in a loss of required separation with an aircraft taking off, intending to take off, landing, or intending to land. It is important to give the same attention to operating on the surface as in other phases of flights. Proper planning can prevent runway incursions and the possibility of a ground collision. A pilot should be aware of the aircraft's position on the surface at all times and be aware of other aircraft and vehicle operations on the airport. At times, towered airports can be busy and taxi instructions complex. In this situation, it may be advisable to write down taxi instructions. The following are some practices to help prevent a runway incursion. Read back all runway crossing and/or hold instructions. Review airport layouts as part of pre-flight planning, before descending to land, and while taxiing as needed. Know airport signage. Review NOTAM for information on runway taxiway closures and construction areas. Request progressive taxi instructions from ATC when unsure of the taxi route. Check for traffic before crossing any runway hold line and before entering a taxiway. Turn on aircraft lights and the rotating beacon or strobe lights while taxiing. When landing, clear the active runway as soon as possible, then wait for taxi instructions before further movement. Study and use proper phraseology in order to understand and respond to ground control instructions. Write down complex taxi instructions at unfamiliar airports. For more detailed information, contact the FAA's Office of Runway Safety and Operational Services website at www.faa.gov/runwaysafety. This tutorial focused on airport operations, both in the air and on the surface. For specific information about an unfamiliar airport, consult the AFD and NOTAMs before flying. For further information regarding procedures discussed in this chapter, refer to 14 CFR Part 91 and the AIM. By adhering to established procedures, both airport operations and safety are enhanced. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.